Hello everyone and welcome back. Today we're going to be focusing on the graphical side of single variable calculus and discuss how the analytical and algebraic side of calculus sort of connects with the graphical interpretation of these particular principles, which can of course lead to better intuition and understanding of the applications that calculus actually gives us. So what I want to do now is just give a basic example of a function that you may encounter, whether it have applications or not. So let's give it some curves there, so possibly a polynomial per se. So I just want to introduce a couple terminology things that I will be using today. And actually, let's assume that this curve actually is not on the entire real line. In particular, the domain is bounded below and bounded above. So when you have a point where it's sort of larger than any point in a local neighborhood of that particular point in its domain, we usually call that location a local maximum. And if you have another point here that is smaller than any point in a local neighborhood of that point, then we call that a local minimum. With this particular understanding, one could of course say that this is also a local minimum since it's smaller than all points in some neighborhood of that point, and also this point right here also would be a local maximum as well because it's larger than all points in some neighborhood of that point. But moreover, these points on the domain actually are larger and smaller than every point in its domain. Therefore, this is also what we refer to as a global maximum since it's larger than all values in the domain, i.e. if I draw a horizontal line that passes to that point, no other point goes above that line, and similar for this local minimum down here in orange. Therefore, that is what we will refer to as a global minimum value. Now, in the case where it doesn't end at either end, then this would have no global min or maximum value, and the same will also be said when you have open endpoints on those ends, because you cannot, if I choose, for example, a point arbitrarily close, you can always choose another point slightly above it that is not exactly at that point, and that point would not be included in the domain, and hence not be included in the definition of global min or global max. Also, each of these curves are functions, but they do not need to be functions when we're talking about minimums and maximums. For example, we could have this type of object, right? So obviously we have a global maximum there. We have a local maximum there, a local minimum there, a local maximum there, a local minimum there, potentially a global minimum as well. And that would be your minimums and maximums of that particular curve. So another definition that is oftenly included, which includes maxima and minima, are what we refer to as extreme values. And extreme values occur at points, for example, x f of x, such that, not therefore, but such that the derivative at that particular point is equal to 0. And in the case of relations, so if we have some point P in some relation R, then the derivative of y with respect to x at that point particular P must be equal to 0 as well. Now keep in mind, just because the derivative is equal to 0 does not imply that it is a maximum or a minimum. For example, let's consider a curve like x cubed or something like that, where it sort of shallows off and its derivative is equal to 0, but it is neither a local max or a local min. So that would be an extreme point that is neither a max or a min. So always keep your mind open to these particular cases. Now, a couple other bits of terminology that I want to introduce are concepts such as increasing, decreasing, concave up, concave down, points of steepest ascent, and points of steepest ascent. So when we look at this particular curve, let's say, and I were to say, okay, is this function increasing or decreasing at that point? Well, if we do a tangent line at that particular point, the slope of that tangent line is positive, which is equivalent to saying that the derivative at that point is positive. We say that the function f is increasing at that particular point. For example, at this point here, if we draw a tangent line, then notice that the slope here is negative, which is equivalent to saying that the derivative at that point is negative. We say that f is decreasing at that point, right? So we have three cases of signs for the derivative. So the derivative can be negative, the derivative can be positive, implying that the function is increasing or decreasing there, or the derivative could be equal to 0, implying that it could be a minimum, or it could be a maximum, or it could be neither of those. Now, let's take a look at another graphical feature that would be important. Now notice that if I draw these tangent lines, for example, here, here, and here, all of those tangent lines are positive, but notice that they are sort of shallowing off until you get to 0. That is, the slopes are decreasing. So the slopes are decreasing as we move from left to right. In particular, they keep on decreasing and decreasing up until some point in the middle, and then the slopes start to, go from extremely negative to 0, and then they get positive and positive and positive, right? So there's some point in between where, for this function, the curve has a point of steepest descent, right? That is, the derivative attains its most negative value somewhere in between that maximum and minimum value, not necessarily exactly between. So notice that if you look at this blue region, it sort of makes the shape of a cave, right? So usually sometimes we refer to this as concave down. Some people also call it concave. And this area in green, notice that if it sort of rains on this particular little hill, the water is going to sort of fill up in that particular region. So it's almost like a cup, and some people will say that that's concave up. Some people also will say just convex, for example. But concave down and concave up are the more commonly used ones. So how can we tell when a function is concave up or concave down? Well, if the derivative is increasing, like in green, then that means the second derivative is going to be positive on that particular interval. And if it's concave down, that means the second derivative is going to be negative at that particular point, implying concave down. And what's between a negative and a positive number? So obviously, points of steepest descent are associated with points such that f double prime of x is equal to 0. We usually call these points inflection points. And inflection points could either be points of steepest ascent, points of steepest descent, or neither of those, similar to the maximum and minimum cases. So those are some of the terminology that we're going to be working with today. Let's actually jump into a couple algebraic examples in order to find, for example, where the extreme points are, where the function is increasing, decreasing, where the inflection points are, and all of those little things as well. As a starting example, let's assume we have the function f of x defined to be 1/3 x cubed minus 5 halves x squared minus 6x, with the domain chosen to be the set of all real numbers. That is, it goes from minus infinity to positive infinity. Let's assume that we first want to find the extreme points for this particular function, implying that we first need to find the derivative first, right? So let's look for the extreme points of this function. Right, so the derivative of this function, so we can just use the power rule in each of these terms. So 3 times 1/3 is 1, and that's going to turn into x squared. 5 halves times 2 is just going to be 5, so we're going to have minus 5x, and the derivative of minus 6x is just going to be equal to minus 6. If you have a polynomial, a very good thing to do first off is to factor it if you can. So, what two numbers multiply to give you -6 and add together to give you -5? So you could, for example, do x minus 6 and x plus 1, because -6 times 1 is -6, and -6 plus 1 is -5. So that is our derivative factored out. So the extreme points are the points where the derivative is equal to 0, which means that x minus 6 times x plus 1 must be equal to 0, implying that our extreme points are x is equal to 6 and x is equal to -1. Once you have your extreme points, then we can classify these as a local maximum, a local minimum, or neither of them, right? So what we can do is we can do a sign chart for this particular curve, because notice that if a point is a local maximum, then it's going to be increasing to the left and decreasing to the right. And if we have a local minimum, then it's going to be decreasing to the left and increasing to the right. So all we need to do is just choose points to the left and right of each of these points, -1 and 6, and then test the derivative at those points, right? So what I'm going to do is I'm going to make a little sign chart. So a sign chart with points -1 and 6 from least to greatest, of course, and we're just going to be picking points here, here, and here, and you can choose any of them because we know polynomial functions are continuous, so any of these points would be fair. So you could choose, for example, -2, 0, and 7 would be reasonable points. So if we evaluate the derivative at -2, that's going to be equal to, and you can plug this into the factored form, for example. You can do -2 minus 6 times -2 plus 1, which is going to be equal to -8 times -1, which is going to be +8. All right, so that's positive. So let's just draw a little upwards, little vector there. Let's do our next chosen point, so f prime of 0. So that's going to be equal to 0 minus 6, 0 plus 1, which is going to be -6 times +1, which is -6, which is negative. So let's draw a little a downwards vector there. And you can probably guess what the next one's going to be. So f prime of 7 is going to be 7 minus 6, 7 plus 1. So it's going to be 1 times 8, which is a positive number. So we can draw that upward vector there. So if we can sort of extrapolate this curve, you can sort of get some idea of what that curve actually looks like, right? So it's increasing at -2, it's decreasing at 0, and it's increasing at 7. That means what? So this means, so we can actually make a few conclusions. That means x equals -1, and we can obviously get the f value as well, is a local maximum, or that point in the domain generates a local maximum. And x is equal to 6 generates, actually I guess you could say generates is a more appropriate word. So x equals 6 generates a local minimum, because you would have to plug in -1 and 6 to get those actual minimum and maximum values. Now we've classified our extreme points, you can also say when this function is decreasing and increasing. So f is increasing on the interval, so it's increasing everywhere from -infinity to -1, and also from 6 to +infinity, because we chose -2 and 7 as the points to test those intervals. And we have also declared that f is decreasing on that interior interval because we chose 0 to represent that interval. So it's going to be decreasing on the interval -1 to 6, and always make sure that these intervals are always open intervals. For the most part, when you have a continuous function, it's always going to be that way. So that's how to classify extreme points, and also how to determine when the function is increasing and decreasing. Now, I just want to mention a couple little subtle details that are very, very important. Keep in mind that we chose the domain for this particular function to be the set of all real numbers, but we don't necessarily have to do that. So let's actually consider an example where it actually looks like the same exact function up front, in particular 1/3 x cubed minus 5/2 x squared minus 6x, with the chosen domain to be equal to -3 and 8. Right? So it's closed on the left and open on the right hand side. So if we were to give this function a quick graph, actually what you're going to see, because if we actually know that -1 is a local maximum from the previous exercise and -1 belongs to that interval, and we also have 6 located here in this particular graph because 6 is in between -3 and 8. So we do have our local min and max from our previous example, but notice that -3 is a lower bound in this particular world. So if we sort of give this a graph, we have our local maximum there. And this function is going to, let's see, it doesn't have a horizontal intercept except 0. So it's going to pass through, and then let's assume that it sort of goes all the way down. Let's assume it goes farther down. I think it does. So let's assume that that's our potential global min. Let's assume it sort of ends somewhere over here at around 8. Right, so let's assume that this is the graph of our function f on our newly classified domain. So obviously this is our local max from before. That is also our local minimum from before. Now in the old example, this did not have a global min because it goes down to -infinity, and it does not have a global max because it goes up to +infinity there. But notice that now our local min is the smallest y value it ever obtains, so it's also a global minimum. And this local max is also a global max because it doesn't attain a value higher than that. So it's also a global maximum, right? But notice that this is now a local minimum, in particular at -3 f of -3, but keep in mind this is not a local max. So you don't need to specify because we're on an open side, right? For the same reasons mentioned above. But I just want to mention this here because it's very, very important to keep in mind. So now that we have that little nuance discussed, let's go back to our original example where we chose the domain to be the set of all real numbers, right? So let's choose the same exact function with the domain to be all real numbers, where f of x was defined to be equal to 1/3 x cubed minus 5/2 x squared minus 6x. So we know how to find the extreme points and identify them. In particular, the main useful tool was the first derivative, which came out to x squared minus 5x minus 6. Now what I want to do is I want to find the inflection points, right? So our goal now is going to be the inflection points. Let's call them inflection points, just like we did in extreme points. And then we're going to classify them as points of steepest ascent, points of steepest descent, and also determine whether the function is concave up or concave down, and when that happens. So in order to do this, our tool is going to be the second derivative. So the second derivative, quite easy, it's going to be just 2x minus 5, and the inflection points occur when the second derivative is equal to 0. And that occurs when 2x minus 5 is equal to 0, which only occurs at one point, which is x is equal to 2.5, or 5/2 as a fraction. So that is our inflection point, so we just need to classify this as a point of steepest ascent or a point of steepest descent. Now let's just draw a quick little graph to get a point of reference here. So if this is the graph of our function, then this will be a point of steepest descent. Notice that it goes from concave down to concave up to imply that that is a point of steepest descent, right? So we're going to pick a point to the left of 5/2, to the right of 5/2, which keep in mind is 2.5. So we can choose, for example, 0 and 3 or 1 and 3. And then we can see if it goes from negative to positive, positive to negative, or it doesn't change sign to the left and right, implying that it's neither of those, right? So let's do a sign chart here. So let's do a sign chart that's built around 5 halves. So we can choose, for example, 0 and 3. So if we choose 0 and 3, what do we get? So f double prime of 0 will be 2 times 0 minus 5, which is minus 5, which is negative. And then f double prime of 3 will be 2 times 3 minus 5, which is 6 minus 5, which is 1, which is a positive, right? So notice that it does go down, and then it goes up, right? So that means for the first derivative, 5 halves is a local minimum, which means that this point is a point of steepest descent, right? So this is the point of steepest descent. Point of steepest descent in terms of x is equal to 5 halves, or it generates a point of steepest descent. Okay, and also from the sign chart we can tell where it's concave down and concave up. So we can say that f is concave down. Keep in mind the breakpoints are going to be the inflection points, and that's going to be on the interval minus infinity to 5 halves, and f is concave up on the interval 5 halves to positive infinity, right? And that's how to do all of those things in terms of inflections, inflection points, points of steepest ascent, points of steepest descent, and telling whether the function is concave up or concave down. Now to add, you can actually avoid sign charts by doing what is called a second and third derivative test for those particular functions. For example, if we have a point that is a local maximum, right? So if f of x is a local maximum, then a couple other things will be true. In particular, the first derivative must be equal to 0, but that's not all that must be true. But the function, notice, is concave down at that point. So if the function has a derivative that's equal to 0 and the second derivative is negative, i.e. it's concave down, then we can classify that point as a local maximum. And similarly, if f of x is a local minimum, then what can you say? Then, well, obviously, the derivative will still be equal to 0, right? So 1 f prime will be equal to 0, and notice that the function will be concave up at that point, which is actually quite interesting. So 2 f double prime will be positive, right? And if it's neither a max or a min, then both the first derivative and second derivative will both be equal to 0, right? So similarly, you can construct, for example, something in regards to the third derivative in order to tell whether a point is a point of steepest ascent or a point of steepest descent, but I will let you figure out those on your own. So this is a brief overview of the graphical things that you definitely should know when it comes to using calculus to analyze curves. Hope you enjoyed this video, and I'll see you in the next one. Take care.